How we doing? I'm Mr. Rose, and today we're going to keep talking about electrostatics, and we're going to talk about a dipole. So here you see a picture of a dipole. In the problem, we say that charge 1 and charge 2, the positive and negative, are separated by a distance of 2a. So I've got A labeled from the center to 1. I can have A labeled from the center to the other, but these two charges are separated by a distance of 2a. And we're just going to explore some of these properties in kind of a simple manner. And I gave this little explanation here, this blurb of charge's position in an external electric field. So that electric field is going to cause some kind of a force on these electric charges, really very similar to what masses do in a gravitational field. So again, we're leaning on a whole bunch of stuff we know and trying to apply it to a harder concept. We're looking for how large is a torque, assuming that the structure is at an angle theta with the electric field. Also, we're going to assume that these two charges are separated by some fixed distance. So, again, let's start discussing the things that I know. What are things that I know about physics that I can apply to this situation? One of the things that I obviously know is that if this thing is going to move, there's going to be a force, and there's an electric force here due to that electric field on a charge. So I know that force is equal to Q times my electric field, right? So that's just saying that there's a force on this charge due to the electric field, likewise up there. Well, I also know that if this thing is like this in this field, because of those charges, it's going to want to rotate in one direction or the other. And that rotating force we know as a torque. And by definition, torque is always then just an R cross F. Right? Simple put, it's our separation distance R, the force on the left, that gives us our torque, or separation distance, the distance from rotation to where it's rotating. And I know that it's just going to be R, F, sine theta. Right? So we know things from mechanics about torque, and we have seen already in the past that torque should be a force times the distance times the sine theta, right? We've shown this to be true for dipoles in the past, specifically in our third lecture video. So this should be something that you should know, and if you don't know it, I advise you to go back and do a little bit of review in that video. Well, what's going on here, right? Like exactly, again, how large is this torque, assuming this structure theta? So how do I do that, right? This is all about that dipole moment, right? Remember, because of that dipole moment, there's going to be this torque that's acting on this entire thing. I'm going to try and draw it out a little bit, maybe just for some simplicity. I'm going to have to do, I'll put something there, I'll put something there. I know that guy is positive, I know that guy is negative. I'll call that a positive Q. Let's call that a negative Q with a force going that way. A force going that way. And based on my picture, that is going to be my electric field. So this is what we're examining here. I know this is my center of mass. Maybe that'll be useful just to know, to understand how this whole system is going. Excuse me. So remember, now our dipole moment is our charge times our distance, right? So I'm going to write that down. My dipole moment, P, let's not confuse that dipole moment P with a momentum, but our dipole moment P is just Q, well, that's supposed to be a Q, D. How is this useful? What is this doing? Well, I know it's got this dipole moment, and I know what's going to happen here is I'm going to try and rearrange such that I can use this D in my dipole moment to figure out what that torque is, right? My torque, which is FD sine theta, well, I need that D. Oh, there we go. Look, there's my separation distance, which is causing this to actually have that torque. So if this was just this one charge, that torque wouldn't exist. So what we're doing here is simple math, simple substitution. My force, we know, force by definition is Q times Z. So the torque is going to be a Q, the charge times my electric field, times that distance. Well, that distance is just my dipole moment over a charge, times my sine theta. Whoop, I don't know if we can see that. I'm just going to rewrite it over here. Times that separation distance, which we rearranged for a dipole moment divided by a charge, times the sine theta. Perfect. All right, and now we can see my charges cancel, and the torque acting on this dipole is simply put my electric field times my dipole moment times the sine of the angle that's acting between what I'm assuming is this rigid body and my electric field. So that should be kind of simple and hopefully understood a little bit. Now, we can also kind of rearrange this and say, wait a second, so this is my electric field, this is my dipole moment, this is a sine, which means my general form, torque, should be my electric field cross my dipole moment. Hey, that could be something powerful to know. And then to figure out our directions, we have to use our right-hand rule, just like we did for any torque. We know that that's supposed to be a positive, that's a negative. There, this is the direction of my dipole moment. So I can say that the torque is equal, I'll say this correctly, the torque, oh, my dipole moment is off the screen. There we go. We want to say that the torque is going to be equal and in the same direction for both charges, right? So for the charge up here and the charge down there, my torque is going to be equal. That makes sense. The magnitude will be equal. And it's going to be in the same direction for both charges. In other words, it's going to cause it to turn in that same direction. So the net torque should be equal to twice the torque on any single object, right? So essentially, is due to symmetry, I'm going to say my net torque is equal to 2 times the torque on any single charge. So again, we're kind of just exploring properties of this dipole within the electric field, which moves me to the second part, which is part B. Part B is actually kind of straightforward, and then we're going to just explore some other stuff about these dipoles, right? So part B, give it a quick case. I'm going to define some magnitudes and tell you define some magnitudes and give you things to substitute in. Torque, by definition, we're looking for the magnitude. We know is, again, R cross F. That's not supposed to be a parenthesis. So plugging in everything that they're going to ask us to plug in this case, the vector R is equal to A. I'm going to say that my torque is equal to 2 times A times QE times the sine of the angle in between times the sine theta. So I know my net torque is equal to 2 times A times Q times whatever that value of the electric field is times the sine of the angle in between. That is a general solution for the torque acting on this dipole moment separated by some distance. And again, it's twice that because my separation distance is 2. And or what we described earlier, because the force is equal in the same direction for both charges, the net torque has to be twice that. What other things can we know about these dipoles? Like, just examine the dipole moment. Give it a little bar. Examine the dipole moment in general, like things to know, right? So first of all, I've said many times, please do not confuse dipole moment P with momentum P. I do not know why they're defined as the same thing, but it is something that's very simple. So torque, general form. What do we know about torque? Our torque in general, regardless of what we're talking about, is just the cross product of A cross B, right? 100%. Now, in this last one, we had A was equal to 2 times A times Q, and our B was equal to the electric field. So this is our general expression, and we can have easily just started with torque and backtrack to get into that way. Additionally, we should know and we should remember that it takes energy to move things, or it takes energy to rotate things, right? So if I want to examine this dipole moment, I can kind of give it a simplistic definition and say this dipole moment is really just some charge times some distance. And the dipole moment is measured in a coulomb times a meter. So because our dipoles have to be separated by some fixed distance, I can, let's say, maybe assume that that fixed distance is going to be a rigid fixed distance. Again, just trying to make some assumptions to make this a little bit easier for us to digest. And if we assume that, then I can say it's going to take work into that field, just like a gravitational field. It's going to take work in that electric field to rotate or to move that dipole. So a rigid body, we know, is the energy, right? The potential energy going from position 2 to position 1 is by definition a change in work, the antiderivative of F dot dr. But here I'm rotating objects, right? So I don't have a linear force that I'm using. I have a twisty or rotational force, which means it's going to take energy due to some external force. That external force is caused by that external field to rotate that object. All right, so we are again applying simple concepts to things that we know to move into this electricity and magnetism world. I hope this is a little bit helpful. I kind of started to riff off the end. Please feel free to like, comment, or subscribe, bring questions, and like always, you will see me next time.